watch after our dogs, because they don't know any better. It's like these hunting dogs and retrieving dogs that are bred to go and go and go. We don't monitor them, they won't monitor themselves. And I used to have a lab that would retrieve and go and go and go until he would black out. That was weird. Murphy's got one like that. So, anyway, dogs. Exponential decay. So do you like the self-correcting worksheets?
Yeah.
Did it help you, do you think? Because that was the kind of stuff that you've been kind of pushing on, and it's been pushing back pretty hard. Did they help you get into a rhythm with that at all?
It helped me. Yeah.
You had one you were going to finish, right? Is that it there? Did you finish that one?
No, I couldn't find it over the weekend.
Oh.
Because I accidentally grabbed my science notebook and not my math. Cause I put it in my math notebook.
How about you guys? Did they help at all, you think? You don't remember it? Oh. Yeah. Think so? Brandon, do you remember it? Not really? Jeez, we should do them again. We're going to do exponential decay. So, in this chapter thus far, you have two formulas. What are they? What are the two formulas we have so far?
Y equals something times 1.
So y equals p parentheses 1 plus r. P.
Then y
Over the yes.
There's something missing from this one. We got most of it.
to the t.
To the t, okay.
And then y equals bg to the x.
Okay. This one, I think we also said a is equal to, for the amount. Okay, I'll write that, but it's the same. It's just a matter of what variables you use. You could call this y equals, well, that would be the x up there, because that goes here, but. What do they have in common in terms of how they get used? They both are for exponential growth. Yeah, that says a lot. Could you use this one on the bottom for money? This one's for money, right? Like if you get interest for something, or even if you have to pay interest on a loan, it works the same way, but we haven't done those questions yet. But this is for like gaining interest on money. What was the one example that we used for this one? Exponential growth of what?
Just population.
Like populations and things, yeah. Okay. But could you use this equation with money? Could you nod in your head? You are. So, like this is the beginning amount of money, P. That would be like the beginning population. But that's the same, it's just a number, it's a starting number. 1 plus R is the same as the growth rate. So when we said that the rapid population was doubling, over like every single year, we were saying that the growth rate was equal to 2. Well, that came from 1 plus 100% growth. You have 100% growth, you're taking the whole population and you're doubling it. So if you change that to a decimal number, it ends up being 1 plus 1, which is equal to 2. And that's your growth rate. If the population grows by a half each period, so like at the end of the year, there are half as many again rabbits. Like if you had 150% of the rabbits each year, then you'd have a growth rate of 1 plus the 50%, which is 1.5. But what if the rabbit population goes down? So if you have something like 100 rabbits to start during that first year, and at the end of the first year, there's only 90 of them left. What can you multiply 100 by to make it into 90? So 100 times what number is equal to 90? How much? 0.09. Like this. How many place values? So then that would be moving it like this. So that would only be 9. So this is close. It's not 0.09, it's 0.9. And what that is 90%. So if you have an example where only 90% of the rabbits remain, what percent do you lose? How much?
10%.
10%. Yeah, so when we say that we're losing 10% every single year, we're keeping 90%. And that's the key with exponential growth. So if we have 10% decrease, that results in 90% remaining. That right there is the most important thing to know when it comes to figuring out what the G value is. So with exponential decay, we do the same thing as with growth. It's just that with decay, G will be less than 1. So if you have 25% decay, you have to multiply by 75% because that's what you're keeping. So let's just go through and do the problem that they have here. This is a good one. Assume that each day after cramming, a student forgets 20% of the vocabulary words learned the day before. And it's probably not too far from the truth. Excuse me. When you cram for tests, you lose it, slowly but surely. If you don't cram for tests, you're less likely to lose it. It sticks longer. So it says, assume that each day after cramming, a student forgets 20% of the vocabulary words learned the day before. And they cram for a French test on Friday by learning 100 vocabulary words Thursday night. But the test gets delayed from Friday to Monday. If the student doesn't study over the weekend, how many are they likely to remember? So, you write, just forget 20% each day. You have 100 vocabulary words. And then you want to know how many are they likely to remember on Monday. So they study on Thursday. Thursday is day 0, and they know 100 words. Friday is day 1, Saturday is day 2, Sunday is day 3. So if they forget 20% of their words, how many will they remember the next day, Friday? So if they forget 20% from Thursday, how many will they remember on Friday? How many? They'll remember 80. So we could say that that's 100 multiplied by 0.8. So they lose 20%, they keep 80%. How many will they remember on Saturday?
60.
How many?
Not 60.
They're gonna remember 80% of 80. So that's taking, here's the 80. And now they're gonna have 80% of that.
64.
So that's 64 words. How many words they lose on the first day? 20. How many they lose the second day?
6.
Only 16. Because they lost 20% of a smaller number. So then by Sunday, how many are they gonna likely remember? What is it?
51.2.
51.2 words, or 52. So that comes from 100 times 0.08 times 0.08. Better put those in parentheses, that'll be easier. Times 0.08 again. So by Monday, how many words? 4 days later. 40.96. So they remember 40 words. So that comes from 100 times 0.8. How many times does 0.8 get multiplied? Once, twice, 3, 4 times. So all we're doing here is we're saying that the ending amount is equal to the beginning amount times the growth rate, which is 0.8 to the x power. So these problems are no different than exponential growth, just that they result in decay. Yeah, I'm going to put my computer up on the smart board. So the next one you have to write the equation for. What's that?
There's a different car in my book.
Is there?
Yeah.
Yeah, the online book has a lot of different stuff. When you get to the geometry book, different books have different pictures. But all the problems are exactly the same. It's kind of funny. So we're looking at example number 2 with the car. What kind of car do you have?
It's almost in
You have a Mustang.
yeah.
But it's the same problem, isn't it? Does it say in 1998 a new car cost?
21,000.
Yeah, so here's an example, $21,000 car in 1998. Gosh, that's 23 years ago, isn't it? Wonder what the average price of a car today is. It's more,
Yeah.
considerably more. Either way, we'll use these numbers. It says, suppose its value depreciates. That means its value goes down. The greatest cost of owning an automobile, in other words, where you lose the most money, is the day you buy a new vehicle. Because if you spent, like this here, $21,000 on a new car, the day you drive it home, it's not worth $21,000. Be honest. If you were gonna buy something brand new, and then you're gonna buy something that somebody owned for a day or a week, would you pay that person who had it for a week the same amount of money as a brand new one? No, nowhere near. So it's like, as soon as people bring a new car home, the price is down, and then it slowly tails off over time.
If they're like crashing, exploding, it's worth nothing.
What's that?
Or if they like crash it and it's worth nothing, and it just blew up and it's worth nothing.
Yeah, that's why when you buy a new vehicle, if you don't pay cash for it, you have to have full coverage insurance on it, or they won't loan you any money. That's a condition of the loan. Anything that you buy, if you are borrowing money, you have to have insurance for it in case you lose it. Car, house, boat, whatever it is. So here, in 1998, a new car costs $21,000, and its value depreciates 15% every year. So if you picture this in a graph, it starts out way up here at 21,000, and it's going to go down a little bit in the first year. But then it's going to be worth less. So when it goes down 15% of this amount, it won't go down quite as much. So what ends up happening is with these depreciation curves, or exponential decay curves, they curve down. As opposed to what we saw with exponential growth, like population growth, that curves up like this. These are going to curve down. So we need to write an equation, and the equation needs to be written in this form. So if we write it y equals, what would be the value we use for B with this car? 21,000. And then what's the growth rate going to be? Since this is a decay, where it depreciates 15% per year. What are we gonna use for the G value? Well, if you use 15%, then the number that you get after 1 year will be only 15% of this. But the car loses 15%. So if we think of this as 100% of the car's worth, $21,000, and this is $0 at 0%, if it loses 15%, how much does it keep? So if we subtract 15% from that car's worth, what percent does it keep? Picture it in here. If all this is $21,000, if I cut out and I remove 15%, what percent remains? 85% remains. So as far as the worth of the car, after 1 year, it keeps 85%. So I don't know, maybe you can write this. For decay G values, what you're gonna do is take 100% and subtract the decay percent. That's what's gonna be equal to G. It's not a growth, it's a decay, but it's less than 1. And when you multiply by numbers less than 1, it makes things smaller and smaller and smaller. So what's missing in the problem, or in the equation? What has to be put in here? To the x power. And x in this case is going to stand for the number of years. So x is the number of years. Y is the value of the car. So here's your equation. And then it says, what was the predicted value of the car in 2005? So if we want the value in 2005, we're going to use this equation, 21,000 times 0.85. So between 1998 and 2005, how many years?
7.
So you're going to use 7. So it's a calculator problem. What do you get? How many dollars is it? Are you playing? 21,000 times 0.85 to the 6,700.
32.11.
So that's what it's worth. So here, then the problem goes, it says, how close is this to the actual price of a 1998 car, which was $7,050 in 2005? So they're going back and they're looking at data and they're saying that that's what cars from 1998 on average were worth. Is this above or below? So it's below. So was the depreciation rate higher or lower than 15%? Did it depreciate more or did it depreciate less? So according to the equation, it says that it should have been worth this much. They're saying that the real data was showing that it was worth $7,050. So, which was more, the depreciation that was predicted, or what actually happened? The prediction was more. So it probably didn't depreciate at quite 15%, something different. So then it says to graph it. And they say with an interval of 0 through 8. So when x is greater than or equal to 0, less than or equal to 8. So they want us to put this onto a grid. So this is going to be years. This is going to be dollars. You guys gonna do this or you gonna watch me? Do you have sticky graph paper? I do it on graph paper. You have no sticky graph paper? Need some graph paper or do you have some? So how are we gonna go about making the data for this? It's a fast, easy way to use this to put together points to graph. You graph it on a calculator. But we still need to make a paper graph with it. So if you're gonna graph it on the calculator, how would you get started, Leo? Yeah, go into y equals. And then when you raise it to the power, raise it to the x power. Plug it in. Oh gosh. Why can't I? Some days I can get this thing there. And then how do you come up with some ordered pairs to be able to put on a graph once you have that put into your calculator? Well, I don't even want you to go to graph yet, okay? It might not graph because of the range. Like your y values are gonna have to start out way up here at $21,000. So once you have the equation put into y equals, how do you find the ordered pairs that you could use to make a paper graph? What, say again?
Just go along the line.
You go along the line if you graph it, yeah, but there's another way. If you look at above the graph, there's a blue word table. If you hit second table, you should come up with x and y values. Does it come up that way?
Yeah.
Are you participating? Yeah, do you have your calculator? Do you have the equation in it? No, you should do that. Turn it on. How do you enter an equation in? Yeah, there you go, that's a start. So then exactly as it is, except make sure when you have the exponent, you use x. We'll start typing. The equation as we have it on the board. So yours started at 0, that goes by 1. So does yours start at 0 and go by 1? Do yours start by 0 and go by 1 also? Oh, you're all the way up to 35 years? So,
I'd rather change the number.
but we're not graphing, Marcus. We're just gonna put the equation in here, and I'll go to the table. So second. There you go. There's, yeah, there's year 0, should be 21,000, and year 1 is 17 something. There you go. So then what you can do is you can just start with this. You start at 21,000. Now, gosh, we want to go out 8 years. So what is the value of this car after 8 years? What does it say? 5,722. So if we started at 21, and then we gotta go down, we gotta get to 5,000. I'm not sure how that's gonna fit on your graph paper. You're probably gonna have to make every line worth several $1,000s. But if I'm just gonna make a rough graph like this, what I might do is break it. And I've gotta get down to what, 5,000 something? So 5,000. So 10, 15, 20. All we want to do is get an idea of what this looks like. So at time 0, it's 21,000. And then go plot each of these points onto your grid. So I'll come out here to 1 year and I'll go up to 17,850, which is right about in here. If you're making a rough graph like what I'm doing there, it doesn't have to be absolutely perfect, just approximate. You guys If you have line graph paper, just gotta figure out how many lines you have vertically and then break that up. So, 1, 2, 3 for every 1, 2, 3, 1, 2, 3, 1, 2, 3. What's that? 5,000 to 10,000 is 3 lines, right? Put 5, 1, 2, 3 lines above the 10,000. And then 15,000 also is 1, 2, 3 lines above. And then we go another 5,000, 1, 2, 3 lines. So you can't change the scale a lot here to make it inconsistent. Do you understand what I mean by that? Okay. If you move 2,000 up, you can approximate that. So you're counting 2,000 for every line. But you don't want to break it here. So that would be 19, that would be 21. Don't break it. Don't, the only place you can break it is on the bottom, from 0 to 5,000. So you're making every 2 lines is equal to 6,000. You're still on the side of that. That's 21, and this is 15, what's this going to have to be? You're going to count by the same amount for each line. So you count every line is 2,000? You don't know? You don't know. All these lines are in. So if this is 5, that's 7. So every line is 2. So that should be 9, 11. What? Yeah, 13, 15, 17, 19. That'd be 21. Oh, that's 21. And then followed by 5. That's another one, that's 2. And then go up this. 15. Will the counter ever be worth 0? Actually, it changes when we get old, but can this ever get to 0? Is he full problem? No, you can't. Because you just keep taking a smaller and smaller and smaller quantity, and that will never be equal to 0. So, let's see, 2. 173. This is about 11. About 93. check your email later today. I'll send you a couple of problems to work on. Yeah, check your email from homework, for homework. Within 20 minutes, I'll have a couple of problems on there for you.